Good day, everyone. This is a continuation of the lecture on Unit 3-1, Regression Analysis. So we continue the lecture by proceeding to the topic of hypothesis testing in multiple regression. Okay, so in hypothesis testing in regression analysis, we basically want to answer the question, how useful is the model? And we can check this through various hypothesis testing procedures. Now, in these hypothesis testing procedures, here are the required assumptions, okay? So it is required that the errors, okay, are normally and independently distributed, okay, normally and independently distributed with a mean of 0 and a variance of sigma squared, okay? And because of this, as a consequence of this, okay, then we also have to assume that y sub I are normally and independently distributed with mean beta naught plus the summation of beta j xij from j equals 1 to k and variance of sigma squared. Now, these are the hypothesis testing methods that we are going to discuss. First is the test of significance of regression, and then we will look into test on individual coefficients and group of coefficients. So let's look at test for significance of regression. Okay, so the question basically here is there a linear relationship between y and a subset of the regressors? So at least one of the regressors. Is there a linear relationship between y and a subset of the regressors? Therefore, your hypotheses are this, okay? So your h naught is such that b1 equals b2 up to bk, okay? So all of the parameters are equal and they are all equal to 0, okay? The alternative hypothesis is that at least one, okay, of your parameters is not equal to 0. So if you reject your null hypothesis here, then you would be able to conclude that at least one of the regressors contributes significantly to the model. Okay, so in test for significance of regression, we remember that the total sum of squares is equal to the regression sum of square plus the error sum of square. Okay, and note that SSR and SSE here are independent. Okay, so SSR is basically the sum of square or the variability due to the regression, okay, or explained by the regression. Now, if H naught is true, okay, then SSR divided by sigma squared is distributed as chi squared sub k with degrees of freedom equal to the number of regressor variables k, okay? And SSE over sigma squared is distributed as chi squared sub n minus k minus 1 with this degrees of freedom equal to n minus k minus 1. Okay. So again, remember that these are the hypotheses that we are testing here in the test of regression and significance of regression. And the test statistic, therefore, is F naught equals SSR over K divided by SSE over N minus K minus 1, which is basically equal to your MSR divided by your MSE. Okay, if F naught is greater than F of alpha, with degrees of freedom k and n minus k minus 1, then you can reject the null hypothesis. Okay, and that would mean that at least one of the parameters, beta sub j, is not 0. Therefore, that means that at least one of the corresponding regressors contributes significantly to the model. Okay, you can also, of course, use the p-value approach. Okay, so you can reject H naught if the p-value for the statistic F naught is less than the significance value alpha. All right. And to compute for the sum of squares, okay, SSR is just equal to beta hat prime, okay, so the transpose of the estimated parameters, times the transpose of X matrix, times Y, which are your response observations, minus the summation of yi from I equals 1 to n squared over n. And then your SSE is equal to the transpose of y times y minus beta hat prime times x prime hat x prime times y. And then SST is just equal to y prime y minus summation of yi squared over n. And of course, most or all of the statistical packages that deal with that has a capacity to deal with regression automatically computes this. Okay, and you can summarize these values in your ANOVA. Okay, for the significance of regression in multiple regression, and it would usually look like this. Okay, so the table would usually look like this. In the first column, you have your source of variation, and then you have sum of squares in the second column, degrees of freedom, mean square, and then F naught. So the sources of variation would include your regression or the model, okay, the error or the residual, and then the total. All right. And these are familiar terms, and you have your F naught here. And of course, in output of statistical softwares, you would usually see the p-value here as well. Okay, so this is a sample output from Minitab for the viscosity regression model that we talked about in the previous lecture video. Okay, so you can see here the regression equation. Okay, so these are the calculated beta, okay, beta estimates. All right, so this is the fitted model. All right, viscosity is equal to 1,566 plus 7.62 times the temperature plus 8.58 times the feed rate. Okay, and again, remember that 7.62 here and 8.58 are the partial regression coefficients. And they are called as such because you interpret each, okay, as the change, okay, expected change in your response variable related to a unique change in the corresponding regressor. So for example, 7.62 here is the expected change in viscosity corresponding to a unique change in temperature holding feed rate constant. And then 8.58 is the expected change in viscosity with a related to a unit change in feed rate while holding temperature constant. Okay, now in relation to the test of significance of regression, okay, so you can see here the ANOVA showing you the regression and then the residual error and total as the sources of variation. And then you have the degrees of freedom, sum of square, mean square, F naught, and then your p-value. Okay, so again, the hypothesis that we are testing is this, okay, or these. And as we said, if F is greater than F of alpha with degrees of freedom k and n minus k minus 1, then we reject the null hypothesis, or if p-value is lower than your significance level. So say your significance level is 5%, okay? So you can see here actually that p is very low, no? It's 0 practically here, which means that we can let go of the null hypothesis or reject the null hypothesis that your beta parameters are equal to 0, which means that at least one of these betas is not equal to 0. And that translates to it being whatever that beta is, okay? It being significant, all right? In explaining, in helping explain the variability in your viscosity, all right? Therefore, we can say, okay, so we go back. Therefore, with that result, we can say that there is a linear relationship between y and at least one of your regressors. So since your p-value is very low, at least one of the regressor variables has a non-zero coefficient. Okay, and you can also see here your r squared. Okay, your r squared here is equal to 92.7. Okay, remember that your r squared, okay, is just equal to your SSR over SST, okay, which is equal to also equal to 1 minus SSE over SST. Okay, and then you can also see here your adjusted r squared. Okay, and it's 91.6. All right, so your adjusted r squared is just equal to 1 minus SSE over the quantity n minus p all over SST over the quantity n minus 1, which is also equal to 1 minus the quantity n minus 1 all over n minus p times the quantity 1 minus r squared. Okay, and we note that when r squared and adjusted r squared differ significantly, it means that it is highly likely that non-significant terms have been included in the models. Okay, now we move on to test on individual coefficients and group of coefficients. So when testing for individual coefficients, the hypothesis that we are testing here is H naught, okay, your null hypothesis is H naught, is that beta sub j is equal to 0, and your alternative hypothesis is that beta sub j is not equal to 0, okay, and the test statistic here is T naught, okay, which is equal to beta sub j hot divided by square root of sigma hot squared times C sub jj, okay, and C sub jj is a diagonal element of the x prime x inverse matrix corresponding to beta hot j. Okay. Now, also remember that your standard error for beta j hot is equal to square root of sigma hot squared times C sub jj. So this is just actually the standard error for beta sub j hot. Okay, now if your the absolute value of your test statistic is greater than T of alpha over 2, okay, with degree of freedom n minus k minus 1, then you can reject your null hypothesis. You can, of course, also use the p-value approach. Now, if the p-value for the statistic T naught, okay, so this should be T naught, is less than the significance value alpha, then you can also reject your null hypothesis. And if you do that, then you can conclude that the parameter beta sub j, okay, is not 0. Okay, therefore, x sub j contributes significantly to the model. Okay, so let's look again at this sample Minitab output for the viscosity regression model. So recall that this is the fitted model, okay, and we are testing individual coefficients here. The coefficients for temperature and feed rate, okay, and as you can see, your p-values are very small, which then leads us to the rejection of two null hypotheses, okay, being beta sub temperature and beta sub feed rate, okay, which means that both of them, okay, both of the coefficients are not equal to 0, and therefore both variables contribute significantly to the model. Both feed rate and temperature contribute significantly to the model. Okay, now let's look at extra sum of squares method. We use this actually to investigate the contribution of a particular regressor variable to the regression sum of squares. Okay, and we can use this when we're trying to investigate the contribution of a variable or a set of variables given the presence already of other regressor variable in the model. Okay, so we recall that y is equal to x beta plus epsilon, okay, where y is an n by 1 matrix, okay, of the response observations, X is an n by p matrix, okay? Beta is p by 1 matrix, and p is equal to k plus 1, okay? K plus 1. Epsilon is an n by 1 matrix, okay? So those are your random errors. And then beta here, let's say that beta is, we can divide, okay? We can divide beta into two sets of coefficients, say beta 1 and beta 2. So one vector corresponding to a subset, the first subset of coefficients, and another vector corresponding to another subset of coefficients. Now, beta 1 is r by 1 and beta 2 is p minus r by 1. Okay, so then y here can, substituting, okay, y here can also be written as x1 beta 1 plus x2 beta 2 plus epsilon. All right, now to determine, for example, whether the first subset of coefficients corresponding to beta 1 here, okay, are significant, okay, our hypotheses are going to be h naught is b1 is equal to 0, okay, and the alternative hypothesis is beta 1 is not equal to 0, okay, and here the test statistic, okay, is f naught is equal to SSR of beta 1 given beta 2, okay, divided by r all over mean square of error. All right. Now, SSR, okay, of beta 1 given beta 2 is just equal to the SSR of beta, so of the full model, minus the SSR with just the coefficients, okay, or the regressor variables corresponding to beta 2. Okay, now, if f naught is greater than f of alpha with degrees of freedom r and n minus p, then we can reject the null hypothesis. And we can also use the p-value approach, okay? So if the p-value for the statistic f naught is less than the significance value alpha, then we can also reject h naught, which would lead us to the conclusion that at least one of the parameters in beta 1, okay, in beta 1 is not 0. Therefore, at least one of the corresponding regressors contributes significantly to the model. Okay, so let's illustrate that in an example. So we go back to the viscosity of a polymer example. Now, suppose that we wish to investigate the contribution of the variable x sub 2, which is the feed rate, to the model. This means that we want to test the hypothesis, okay? H naught is that beta 2 is equal to 1 and H1 where beta 2 is not equal to, okay. H naught where beta 2 is equal to 0 and H1 where beta 2 is not equal to 0, okay? Recall that we have 16 observations on the viscosity of a polymer denoted as y and two process variables where reaction temperature is denoted as x1 and catalyst feed rate denoted as x2. And these are the data. Okay, so you have 16 observations, observation for temperature and catalyst for each observed value of viscosity. Okay, and viscosity is in centistoles. Now, to perform extra sum of squares due to feed rate, okay, we first get SSR, okay, of beta 2 given beta 1, beta naught, which means that we basically get the SSR, okay, when we add beta 2 to a model where we already have beta 1 and beta naught. In other words, we want to see how much the contribution of feed rate is, okay, when we already have a model, okay, to begin with, where the variable includes your temperature, okay. So to get that, you just subtract, okay, the SSR, okay, so the sum of square due to regression, where you have the simple model, okay, so you only have temperature, okay, from the full model where you have where you included your catalyst feed rate. All right, so that would be equal to SSR of beta 1 and beta 2 given beta naught minus SSR of beta 2 given beta naught. Okay, so from the mini-top output, okay, you can see here the regression sum of square. Okay, that is basically your SSR of beta 1, beta 2 given beta naught. Okay, and so basically the sum of square due to the model, which is the full model in this case. And the degree of freedom here is equal to 2. Now, the reduced model, we only have the temperature, okay, would be y equals beta naught plus beta 1, x1 plus epsilon, okay? And the fitted model for this is, if we run the data, okay, if we fit this simple model to the data, the fitted model would be this one, okay? And the SSR for this model would be equal to 40,840.8. The degree of freedom is equal to 1. By the way, you can also find that in the Minitab output down here. It says sequential sum of square. Okay, so if you only have temperature, okay, then your sequential sum of square would be 40,841. Okay, so that's SSR beta 1 given beta naught. All right. So now let's get SSR of beta 2 given beta naught and beta 1. All right. So again, this is equal to the sum of square due to regression for the full model minus the sum of square due to regression of the reduced model where we only have temperature. And that would be equal to 3,316.3. And the degree of freedom for this is 2 minus 1, which is equal to 1. You can also see this in the Minitab output, okay, the sequential sum of square where we added feed rate, okay, and this is the sequential sum of square. Okay, so now we are ready to compute for the test statistic F naught, okay, and this is equal to SSR of beta 2 given beta naught beta 1 divided by your degree of freedom, which is 1 here, all over your mean square of error. And note that the MSE here should be obtained from the full model. Okay, so we get 268 here. And so we have these values, and we get F naught is equal to 12.3926. Now F of alpha, okay, with degrees of freedom 1 and 13 is just equal to 4.67. And we can see that our test statistic F naught is much greater than this value. Therefore, okay, since F naught is much greater than F of alpha with degrees of freedom k and n minus k minus 1, then, okay, then we reject the null hypothesis. Okay, reject the null hypothesis, which leads us to the conclusion that feed rate contributes significantly to the model. Okay, so now we proceed to confidence intervals in multiple regression. Okay, so again, it is important to note that it is required in deriving the confidence interval that this assumption can be upheld. Okay, the assumption that the errors are normally and independently distributed with mean 0 and variance sigma squared. Okay. Also, beta hat is normally distributed with mean beta and variance sigma squared, okay, times the inverse of the x prime x matrix. Okay, so beta j hat minus beta sub j all over square root of sigma squared, sigma hat squared c sub jj, okay, from j equals 0 to k is t-distributed, okay, with n minus p degrees of freedom. Okay, recall again that c sub jj here is the jjth element of the inverse of the x prime x matrix, and sigma hat squared is just the estimate of the error variance. Okay, so sigma hat squared here, is equal to SSE divided by n minus p. Okay, now to compute for your confidence interval, okay, so for the 100 times 1 minus alpha confidence interval of your individual regression coefficients, you can just use this formula, all right? So your beta j, okay, should be greater than or equal to beta j hat minus t of alpha over 2 with degree of freedom n minus p times the square root of sigma hat squared c sub jj, okay, and less than or equal to beta j hat plus t of alpha over 2 with degree of freedom n minus p times square root of sigma hat squared c sub jj, okay? So this would be the lower and upper values of the 100 times 1 minus alpha confidence interval. So recall that the standard error of beta j hat is just equal to your square root of sigma hat squared c sub jj. Okay, and this is usually shown in your statistical package outputs. Okay, so this can be simplified to this. Alright, so let's go back to the viscosity of polymer example. And let's try to construct a 95% confidence interval for the coefficient of temperature. So the parameter beta 1. Okay, so we can see here the temperature, okay, is 7, the coefficient for temperature is 7.6213. Okay, so beta 1 hat is 7.6213. Okay, and sigma hat squared is just equal to 267.604. Okay, so here. And C11 from your inverse of the x prime x matrix is just 1.49184 times 10 to the negative 3. Okay, so we can use those values and input them in the equation that I just showed you earlier. Okay, and from there we can get the confidence interval for beta 1, which is 6.2855 to 8.950. So this is the 95% confidence interval. Okay, so since we used an alpha of 5% here. So notice here, this is alpha over 2, this is alpha over 2. Okay, so this is the 95% confidence interval, okay, of your beta 1. Which means that if you had, for example, a 100, okay, 100 samples, okay, not sample size, samples, in 95 of those samples, okay, your beta would fall within, beta 1 would fall within these values. We can also estimate the 100 times 1 minus alpha confidence interval on the mean response, okay? So, say that we want to get, okay, to estimate the confidence interval on the mean response for this point here. Your point being expressed in this matrix. So x naught is equal to 1, x naught 1, and so on. All right. So these are particular values of your regression coefficients. These are particular values of your regressor variables, I should say. And then your mu y given x naught, okay, is the mean response, right? Mean response given this point here in the design space. This is equal to beta naught plus beta 1 x naught 1 plus beta 2 x naught 2, and so on. Okay, and this can be expressed in matrix form as x naught prime beta. All right. So y hat of x naught is equal to x naught prime beta hat. Now the expected value. Okay, so we want to get the expected value, okay, of y hat as a function of x naught. And this is just equal to the expected value of this expression here as well. And this is equal to x naught prime beta, because we know that beta hat is an unbiased estimator for beta, right? Okay, so this one is equal to mu of y given x naught. And your variance of y hat of x naught is equal to sigma squared x naught prime times the inverse of x prime x times x naught. Okay, now given those, then we can estimate, okay, we can compute for the 100 minus times 1 minus alpha confidence interval of your mean response, okay, by using this equation here. All right. So now prediction, let's proceed to prediction of new response observations. So to predict new response observations, we can just use this formula over here. This should be minus, okay? Now, it's important to note that you have to be careful not to extrapolate beyond the region containing the original observations because your fitted model might not be good, okay, in representing the behavior of points beyond your design space. Okay, so let's illustrate, okay, what we've just discussed using the filtration rate of a chemical product example. So recall this example, okay, we've been using it a lot in our previous discussions. Okay, so you have chemical products produced in a pressure vessel, okay, and you have, we talked about a factorial experiment, okay, being carried out in a pilot plant to study the factors thought to influence the filtration rate of the product. The 4 factors are temperature A, pressure B, concentration of formaldehyde C, and stirring rate D. Each factor is present at 2 levels. The design matrix and the response data obtained from a single replicate of the 2 to the 4 experiment are shown in the following table. And the 16 runs are made in random order. The process engineer is interested in maximizing the filtration rate. Current process conditions give filtration rates of around 75 gallons per hour. And the process also currently uses a concentration of formaldehyde factor at high level. Now, the engineer would like to reduce the formaldehyde concentration as much as possible, but has been unable to do so because it always results in lower filtration rates. So we want to maximize filtration rate and we want to reduce formaldehyde concentration. So these are the observed values of the filtration rate for each of these combinations in the factorial experiment. Now, recall that we were able to find that factors A, C, and D were significant, and the interaction between A and C as well as A and D were also found to be important. So that's main effects, the main effects of the temperature, the concentration of formaldehyde, the stirring rate, and then the interaction between temperature and concentration of formaldehyde, as well as the interaction between temperature and stirring rate were found to be important. Okay, and from there from the main effects, okay, we were able to derive also the coefficients for our regression model. Okay, so this is the fitted model representing, okay, so this is the empirical model representing our findings from the factorial experiment. Okay. Now, given what we want to achieve in this experiment, okay, if say we want to perform a confirmation run, a reasonable confirmation run, okay, would be one where we have A, B, and D at high and C at low level, okay, because remember the engineer wants to reduce the concentration of formaldehyde, okay. Now, if the fractional factorial has been interpreted correctly and the model is valid, so this one, the observed value at the point of interest should fall within the confidence interval. So the point of interest being x1 be equal to 1, x2 be equal to 1, x4 be equal to 1, and x3 be equal to -1. So remember that our x's here are coded variables. Okay. Okay. With this and using our fitted model, okay, we get an estimated response of 100.25. Now, suppose that the observed value is 104. Okay, we can now use this formula to obtain the confidence interval. Okay, and our confidence interval is from 90 to 100. Okay, so we are using here a 5% significance level. Therefore, this is a 95% confidence interval. Our 95% confidence interval is from 90 to 110.5. Since the observed value falls within the confidence interval, this confirms that the fractional factorial was interpreted correctly and the model is valid. Okay, now we proceed to regression model diagnostics. So we want to answer two main questions. First, does the fitted model provide an adequate approximation to the true system? So that's the first one. And the second is, are the least squares regression assumptions not violated? Okay, and these are our main tools for now for model diagnostics. You have residual plots, as we've been using in the previous lectures. And then you have scaled residuals and PRESS. And then you have your influence diagnostics. Okay, so let's start with... Okay, so we're not going to discuss any more residual plots since we've used that several times in the past. Okay, let's move directly to scaled residuals and PRESS. Okay, let's start with scaled residuals. So one method to scale residuals is standardized residual. Okay, so your standardized residual is basically this one, no? So represented by D sub I here, which is equal to E sub I divided by sigma hat. Okay, from I equals 1 to n. And your sigma hat is just equal to the square root of your mean square of error. And the mean for this is 0 and the variance is approximately 1. Therefore, okay, so this is useful in spotting outliers, by the way. Okay, now, since these are the parameters for the distribution of your D sub I, okay, your potential outlier can be spotted if it is beyond the following range, okay, where D sub I is greater than or equal to -3 and less than or equal to 3. Okay, so what do you do once you spot the outlier? So it is important that you investigate the outlier because it might signal problems that range from measurement or recording error to inadequacy of the model in some region of the regressor variable space, meaning your fitted model might not be adequate in that particular region where you found the outlier. Okay, the next method for scaling residuals is the studentized residual. Okay, and this is recommended way of scaling residuals. So your studentized residual R sub I is equal to E sub I divided by square root of sigma hat squared times the quantity 1 minus H sub II. Okay, where E is just equal to your observed minus your predicted. Okay, and your sigma hat squared is just equal to your MSE. Now, this takes into account the inequality of variance, okay, from your data. And note that we have to do this because usually there is less variability close to the center of your design space, okay? And we have to take that inequality into account because those that are farther from the center of the X space would have higher variability. Okay, next we talk about prediction error sum of squares. Okay, so this one is useful in providing us an insight as to how well your model can predict the value of your response variable given new set of values for your regressor variables. Okay, so PRESS is just equal to the summation of E sub I squared, okay, where E sub I is equal to Y sub I Okay, so observed minus predicted. Okay, so summation of the square of all of that. And your R squared prediction is just equal to 1 minus your press divided by your total sum of square. All right? So for our example, for our viscosity example, okay, the computed press would be 5207.7 and the SST is 47,635.9. Therefore, the prediction R squared is 89.07, which means that the model is good in providing estimates of the response variable given new set of data. Okay. Now let's move on to influence diagnostics. Okay. As I mentioned earlier, there is inequality in variability in terms of how far, with respect to how far the points are from the center of the design space. And the remote points, okay, in the design space can actually have high influence on the parameter estimates, right? Or we can also say that the remote points have leverage on the parameter space, on the parameter estimates. Now, let's just define here the HAT matrix, which is very useful in determining high leverage points. H is equal to X times the inverse of X prime X times X prime. Okay. Now, if a diagonal element H sub II is greater than 2 times P over N, then the observation I is a high leverage point. Okay. So this is an output, okay, for computer output corresponding to our viscosity example. Okay, so here you have the observation number, you have the observed value for y sub I, you have the predicted value given your fitted model, you have your residuals, which is basically y sub I minus yi hat, and then you have your h sub ii. Okay, so these are the H sub ii element of the HAT matrix. Okay, and again, we use that to determine, okay, the influence of the different points. Okay, and then you have your studentized residual, you have your standardized residual. Okay, and so, okay, looking at the column on H sub ii, okay, these are the values. Now, as we said earlier, if any of these H sub ii is greater than 2p over n, then that means that the corresponding point is a leverage point, okay? So 2p over n is equal to 0.375 in this case, okay? So that's 2 times 3 divided by 16. So looking at the values under the H sub ii column, you can see that no observation, okay, is greater than 0.375. Therefore, there are no leverage points in this data. Okay. Next, we test for lack of fit. All right. So first, we define SSE being equal to SS sub PE plus SS LOF. Okay, so this is sum of square due to pure error, and this is sum of square due to lack of fit. All right, so the sum of square due to pure error can be computed as such. So you have the square of summation over n and m, okay, of y sub ij minus y bar I, okay, squared. And this one is equal to n summation of ni times the quantity y bar I minus y hat I squared from I equals 1 to m. Okay. If f naught here is too large, then it means that that there is lack of fit basically. So how do you compute for f naught? It's ss lack of fit divided by the quantity m minus p all over ss pure error divided by the quantity n minus m. And this is just equal to your ms LOF divided by ms PE. Okay, so if there is lack of fit, okay, then the regression is not linear. Okay, and how do you know that? That's when your F naught is greater than F of alpha with degrees of freedom M minus P and N minus M. Now, what do you do if you get this result? You have to abandon the model, no, the fitted model, and find a more suitable one. So you have to iterate. Okay, so that wraps up the discussion on regression analysis. Okay, so the topics that we have covered under regression analysis are as follows. We have model fitting, and then we talked about hypothesis testing. We talked about confidence interval estimation, and then we also talked about model adequacy checking. In the succeeding lecture, we're going to tackle the last topic of this semester, which is Unit 3-2, Response Service Method.